Good morning, everyone. Welcome to the second day of the second week of the Coding CHPC NITheCS summer school. And today we're very happy to have Professor Uwe Jaekel with us, who will going to give us lectures and tutorial today on probability and statistics. And on Thursday, he will also tell us a little bit about the partial differential equations. And Professor Uwe Jaekel is a professor of mathematics from Germany, from Koblenz University of Applied Sciences. And he is astrophysicist by training, and he worked as a researcher in academia and industry, but now primarily he is doing a lot of computational physics, and we're very happy that he kindly agreed to give us and help us with these lectures. Thank you very much. Take it away, Uwe.
Okay, thank you very much, Ilya, for the introduction. Hello, welcome from me. I'm about to say a few things about probability and statistics in the first part, and it's all aiming towards a Monte Carlo method. So it's what I tell you about probability and statistics, that's mostly with the application of Monte Carlo in mind to solve computational problems. Yeah, and that's what I've done as a day job, also in industry. And so before I return to academia. The slides, I'm working mostly with a Jupyter notebook, and the notebook is available on Canvas, as you probably see. And let me just start with a few practical things. I assume that you, maybe some of you want to do the same thing as I do on their own computers. Maybe not, and but if you run into problems, so then there might be a few, and I try to make you aware of some of them. Yeah, I also try to keep the chat inside, so if there are any questions or trouble, then please let me know, and maybe or someone could alert me if there's something coming up in the chat. So I'm using Jupyter Labs. Others of you might use Jupyter Notebook, and those who are using Jupyter Notebook might run into problems with this part here. Yeah, so this is basically about the. I guess most of the stuff that's reading here that you can see here, importing some basic libraries that we need. I would try to restrict it. Most of the time, I don't want to overwhelm you with libraries, so I will restrict myself to using NumPy for the numerics and Matplotlib for the plotting. And I do a little bit, but that's just for this purpose. I do a little bit of interactive stuff with IPy widgets. Yeah, so, and for Matplotlib, the representation is nicer with Matplotlib widgets, and if you're using Jupyter Lab. So I imported this. If you run into problems, yeah, so if you run this slide, there might be an error code, and if you see an error, just feel free to replace the, as I have documented here, replace the widget with inline. Yeah. Okay. So after the, I guess this should be the only problem that shows up. Huh? Otherwise, I try to restrict myself to very standard stuff. And then let me start with the official presentation. So it's the presentation is started. It's the same notebook, yeah, that I use for the presentation. So I start with a short reminder on some facts on probability and statistics. Yeah, and we have to cope with random numbers. And first question we might ask ourselves is, can we actually create random numbers on a computer, or invent our own random numbers? That's difficult. If you should come up with a random number, let's say between 1 and 10, you would probably not have a uniform distribution. You know, if I say, pick any number with the same probability between 1 and 10, or even a sequence of 100 random numbers, yeah, then humans tend to underestimate the probability that, for instance, there are 3 tens following after each other. Yeah? So 10 is the upper limit, and it actually may happen that you have 3 of these 10s in a row. And as a human who should create a series of 100 random numbers, you would probably not come to this idea. You probably can find papers about this, or make an experiment with this. And actually, you have seen deterministic algorithms, quite a lot of deterministic algorithms probably over the course of this, over the last week and this week. And these were deterministic algorithms. So you should ask yourself, okay, I have something deterministic. How can a random number emerge from that? Yeah, and that's actually not an easy problem. And real random numbers are a valuable resource in a way. There are some so-called physical random number generators. So this could be, for instance, shot noise in electronic circuits. Yeah, so there are, it can be cosmic rays. Yeah, for instance, I've recently read a paper about encoding, a coding scheme, exchange of, thank you very much. I just got the program. So, okay, you can use cosmic rays. When do cosmic rays, when and where do cosmic rays enter into my machine or into my detector? From this, you can create random numbers. And the purest form of random numbers are actually quantum random number generators. Yeah? For instance, if you know something about quantum mechanics, the Schrödinger cat, or there's a quantum coin flip. Yeah, there's a probability that of say 50% that the coin, or that's for no, sorry, it's not a quantum coin, might be a spin one, that the spin points upwards or downwards. Yeah? And for all what we know, this is the purest form of random numbers. So in a way, I think quantum mechanics is the only part where real chance enters into science. You know, most of other components to science are deterministic in a way. Okay, so with a deterministic algorithm, we cannot really create random numbers. So because when we start the algorithm and start the same algorithm again, the same output should come. Yeah? So in a way, it's not what you would understand as a random number. But there's a thing which is for computational purposes as good as for all what we know. Some of them have the limitations, but you can use for most cases these pseudo-random numbers, random number generators, PRNG, very nicely. These are, I don't have the time to talk about how to generate these random numbers, but these are deterministic sequences, highly nonlinear functions of basically what is behind that is integer arithmetics. Yeah? And they turn these integers into floating point numbers for our purposes in most cases. But it's very hard to predict the next random number from the previous random number, or from a sequence of previous random numbers. Now so actually these random number generators compute the next random number from the previous ones, but it's a very complicated and involved algorithm, such that you as a human being, or you cannot usually you cannot reverse it. Yeah, so these random numbers appear random for all practical purposes to us. And if you find something that some notable difference with random number generator from what you expect from random numbers and what is proven for real random numbers, then you have to work on your algorithm again. Yeah, this has happened in the past several times. People found, oh, if I have a look at it in 3D, I suddenly see correlations between the sequences of random numbers, and this is not nice. So I have to get a more complicated sequence. There's one important distinction that you should know. What I will talk about and what Monte Carlo methods actually are mostly about are so-called pseudo-random numbers, this here. And these are random numbers as close as possible to actual random numbers. They are used in Monte Carlo methods. There's another interesting, very nice topic, but not our topic today, called quasi-random numbers. So these numbers also look a bit random, but actually they are not. Yeah, they are not independent, while the pseudo-random numbers create numbers that appear independent. Yeah, and I will show you in a minute what's the main difference between these kind of random numbers. They are also called low discrepancy series. Because the idea is that you fill the space with kind of randomish numbers, but actually they are not real random numbers, but they try to fill the space much more uniformly than pseudo-random numbers. And the nice thing about these pseudo-random numbers, and these are filled for themselves, or the main application is quasi Monte Carlo methods. So it inherits this quasi from the random number generator, and these have sometimes more sometimes nicer convergence properties than Monte Carlo methods. Maybe I can come back to this a bit later. It's an interesting topic. It works sometimes really nicely, but the reason why I'm not a huge fan of pseudo-random numbers is they are a little bit harder to use universally, and in particular for very high-dimensional problems. I'm interested in very high-dimensional problems. They are not the best choice. Yeah, so they cannot beat Monte Carlo in some cases. So Monte Carlo is it's a bit more robust. Sometimes it's not the nicest methods you can come up with, but it's a pretty simple method, or it gives rise to some pretty simple methods that are really usable, and sometimes you can get better results with quasi Monte Carlo. So just that you know it. Oops, okay, and now there's the first problem, because I wanted to show you some, let's see. The SciPy package contains a subpackage stats for statistics, and there you have QMC for quasi Monte Carlo, and there you can create. Yeah, you can look it up into the. We don't have to look into it. I just want to show you the difference. Here, what real random numbers, for instance, generated with a quantum random number generator or a pseudo-random number generator, as we use it in a second, the random numbers fill the space like this. Let me make this a little bit larger. And you see, if it's really random, you see there tend to be clusters, regions which are pretty well explored, while other regions look a bit emptier. Yeah, and the idea of the quasi-random numbers, I will not talk how these are generated, but the idea is to put the next random number at a position where it tries to fill the gaps as evenly as possible. Yeah, here this looks a little bit empty, and this looks a little bit empty, and this. Yeah, so the next random numbers would be preferably inserted into this space. Yeah, yeah. and with a nice distance to the others. Huh? While this here is really blind. A new random number generated doesn't care at all whether another random number has been created in the vicinity. Yeah? Hope you see the difference. So the quasi-random numbers explore the space much more evenly. And yes, and say you have a function that you want to explore or integrate, for instance, we will talk about Monte Carlo integration later. Then it's nice to explore the function more evenly, and here it's here you have a good exploration of the function. Here you have a poor exploration, and this is a kind of trade-off with quasi-random numbers, which is in many cases very nice. Excuse me. Somehow. Yeah, so let's talk a little bit about distributions of random variables. Mostly we will talk about random numbers. We will think about random numbers, but actually it can also be letters or something like that. So let's say we have a finite or countable set of potential values of a random variable. Think in numbers. We call these x1 to xm. So then we have a finite set of numbers, so m possible outcomes. Or it could extend to infinity, no? But we can count it. It's countable. We can say this is the first one, this is the second one, this is the 100,000s, and so on. But it may be infinite, maybe not. And the probability of an outcome, mathematically, it's very easy. We can call it a probability if it fulfills only two conditions. First, it has to be non-negative. Yeah, so it can be zero. Probability of an event can be zero. Yeah, for instance, the event could be that the number is 1 and the number is even, but 1 is not even. Yeah, so this is would be a crazy event. It's logically not consistent, but so therefore the probability is 0. So I'm also I'm losing a bit loose mathematical notation. I will just not distinguish between random variables, events, and so on. I'm a bit sloppy about this. Yeah. So the probability has to be a positive or 0 or positive. It cannot be negative. And all the probabilities must sum up to 1. Yeah, to 100% or 1. Yeah. These are the only probabilities that mathematicians require from probability distributions. Now, how can we sample from discrete distributions? And this is a coding school. And it's good practice when you are doing Monte Carlo methods, or later we will talk about machine learning, to make your code reproducible, yeah, such that everybody can control what was your computation, and everybody on every machine would get the same results. Yeah, and Python has come quite far with it. Python and other languages. So usually, I guess if you are on, yeah, I tried it on different platforms. If you do the very same calculations, I'm currently working on a MacBook. If you do doing the same, not on a Mac, but on a Windows machine or a Linux machine, or even on a smartphone, you will get the same results if you set the seed number. Yeah, so this initiates this deterministic algorithm with the seed, and there are some popular seed. 42 due to Douglas Adams is one of the more popular ones. Yeah, others take 1, 2, 3 or 1 or whatever. You can insert your favorite number. Yeah, so this initiates the random number generator, and as I told you, it's a deterministic algorithm. So if I roll dice for 10 times now, yeah, as I simulated by rolling dice, it should be a number between 1 and 7. Sorry, between 1 and 6. And as you know from Python, the lower limit is included and the upper is excluded. Yeah, so this is a random number between 1 and 6, and I want to have 10 of them. Yeah, so that's how you sample it. Yeah, I run it again, and I run it again, and you see the output doesn't change. Yeah, if I change the random number, yeah, even let's take 43. Yeah, if it's very sensitive to changes, you will get a completely different set of random numbers. Yeah, but again, if I set the seed with to 43, I will get the same sequence again. You only do it once, yeah. It's important not to do it every time, because if you do it every time, you would get the same output again. Yeah? So let me replace it with 42 again. So it's a bit noisy, I hope. But okay, I said roll a die, and you know, dices are supposed to have equal probabilities. The probability to show a 6 should be the same as the probability to show a 7 if you have fair dices, fair dice. What if you don't have this equal probabilities, which is, you know, for instance, let's say you have an you want to choose randomly between bananas, apples, and cherries, and you have a preference for one of these fruits. Yeah. Yeah, so here's a Python implementation how you can do this. Yeah, let's say apple, banana, cherry are the fruits, and you happen to like, maybe it's not your preference, but you happen to like apples the most, and banana are okay, and cherry not so great, but okay, every once in a while I can take a cherry, pick a cherry. Okay, it's a new meaning of cherry picking. So the probabilities have to sum up to 1, and this is fulfilled here. Yeah. And now we draw 30 fruits with these probabilities. Yeah? For 1 month, we want to have our fruit planning in the morning. Yeah, we make it on 1st of February or 1st of March. Yeah, and then we get this result. Now, I didn't reinitiate the random number generator. Yeah, so because and that's why on every run I will get a new choice. Yeah, and you see, there's if you look at it, there's a preference of apples, as one should expect. Yeah, and cherries are occur less often. Sorry, I have to run every line of Python, but that's not. And we can make a nice histogram of that. I assume that you are familiar with histograms. Yeah? So we have had 18 apples, 10 bananas, and 2 cherries on our menu, on our month menu. Okay. Of course, you can do it also with other. Okay, so I think this is useless. Let me just see what I've. Okay, yeah. Okay, this is not really necessary. Okay, these are discrete distributions. I hope. So this is the simplest case. We select from a discrete set. But in many applications, you have continuous distributions with density functions. And let me briefly repeat what is a probability density function. a probability density function that's also determining that it's a function of if you want to determine that the value of the random variable, the random variables, so before you select it, it's a random variable, and these are usually called denoted with capital letters in statistics and probability theory. Yeah, so don't worry too much about that. It's just the standard notation. Yeah, so the probability that your random variable is between x1 and x2. Yeah, don't worry if you have learned anything where you have instead of less than, that you have less than or equal, less than or equal. It doesn't make a difference for continuous distributions. Yeah. So the probability that the random variable lands in the interval between x1 and x2, this is just the integral over the probability density function. Yeah. And for small intervals, maybe you have heard this definition. Let's say we have a very small value delta x, the width of the interval, and the probability that the random variable land in the interval x to x plus delta x is the integral again. But the integral, if the function doesn't vary very much, so delta x is very small such that this is practically a constant, then you can put this before the integral, and you get that this is just p of x times delta x. So I see something in the chat. Okay. Okay, it's taken care of. Yeah, if the module is not found, then it should come with my matplotlib actually, but yeah, sorry that I cannot help it at this moment. Yeah, it probably means that the module is not installed. Okay. Yes. So it's the density times the size of the interval. This is the probability that the random variable lands in this place. Yeah. So let's demonstrate this for the normal distribution. This bell-shaped curve that everybody knows about. Oops, there's something bad is happening here. Okay, maybe I'll just leave for a second, go back to the Jupyter notebook itself to show you the interactive part. Yeah. So here we have the standard normal distribution. That's the probability density of the standard normal distribution. And what I've done here is to write a small widget. If you like to do this yourself, here's the code. It's in the notebook, but we don't have to care at the moment. So W is the width of the interval. Yeah, it's from minus W to W. I integrate. Yes. So for instance, here I start with an interval size of 0.05. We see that the probability density at 0 is around 0.4, right? And the orange thing is the interval. Sorry, I messed up my screen settings here somehow. Oh, that's too bad. Don't know what happened here. Actually, let me try matplotlib widgets. maybe this helps. Matplotlib inline. Okay, this works better, I hope. Let's see. Yes, it works. Yeah. Okay. So here I have, for instance, so the probability, this will be the probability is the area under so this orange area under the Gauss curve is the probability that the function will have a value between minus 1.73 and plus 1.73. Yeah, and the probability is 91%. Or almost 92%, yeah. And let's start go to the start. We start with let's say we start with no 0.0. Then the probability to be exactly at 0 is 0. The probability to be let's say at that it is between. Let me. Yeah. That it's between minus 0.05 and plus 0.05. Yeah, then the width of the interval is 0.1, and the probability, if this interval is small, that should be the probability at 0, yeah, which is about 0.4 times the interval width, and so this probability should be very close to 0.4 times the width of the interval, which is 0.1. And you see here, I computed it for you. The area is actually 0.04. Yeah? That means 4% probability that the value will land in this interval. And we can just reproduce a few well-known results that you should have learned in your statistics class or probability theory class. Yeah, for instance, this is a standard normal distribution. That means it has a standard deviation 1 or variance 1 and mean 0. Yeah, and around 68%. Yeah, I guess you should have seen this at some place in your math or statistics education. 68% of the values are lying in this interval. Yeah, between 1 standard deviation from the mean, plus or minus 1 standard deviation within plus or minus 1 standard deviations from separated from the mean. Yeah, that's a standard result. Yeah. Okay. Okay. I try to answer this question concerning widget and inline. If you install Jupyter Notebook, this and Matplotlib, yeah, then I guess it if these have been installed, you should be fine. Right? So Jupyter should be installed and Matplotlib, and then everything should be fine, I guess. Yeah. So yeah, another important result, maybe that you may have heard about. 95% confidence intervals. Yeah, what is the 95% confidence interval? We increase it such that 95% of the values are lying inside this region. Yeah, let me increase it and increase it. Yeah, so And at some stage here, so here we're getting a little bit bigger, approximately at 1.96 standard deviations, or almost -2 or +2 standard deviations distance from the mean, you have 95% of the values inside, okay? Yeah, and this is the 95% confidence interval that you know. So there are some, there's a 5% probability that the value is smaller than minus 1.96 or larger than 1.96 times the standard deviation. But the bulk of the data is lying in this interval. Yeah? If you are drawing, if you sample from a from the normal distribution. Okay, then let me try to get back to my slide presentation. Okay, great that you sorted it out. Okay, so how can we sample from continuous distributions? Let's say there are, if you are working with random numbers, there are two distributions you have to know how to sample from it, and you have to know how to do it in the language that you are using. Yeah, and here we are using Python. And let's assume that we are sampling from a uniform distribution between 0 and 1. And so we want to have a number between 0 and 1, but it should have the same probability for every number in this interval. Yes, probability of 0.01 should be the same as the probability of 0.73598. Yeah. And the way to do it in, or one of the ways to do it in NumPy, and it looks very similar in other implementation, other libraries, in JAX or in Torch, TensorFlow, that we will hear later about. The way is the function rand. Yeah? The function rand is included in NumPy. I have imported NumPy as NP. So if you just type import NumPy, then you would have to replace this NP with NumPy. It contains a submodule called random. And this has a function rand. Yeah? And if you enter two numbers, yeah, if you just type rand, it will give you one random number between 0 and 1. Oh, 0 and 1. Random number again, and you see it's coming from a wide range. If you specify two arguments, if you specify one argument, it will create a vector of this length. Yeah, you create 3 random numbers at a time. You can also give it 2 arguments. Okay, something's wrong. Oh, that's too bad. My comma is broken. That's a catastrophe. Sorry. I didn't expect that.
Sorry, copy comma from the line below. Okay, that's an excellent idea. Okay, I just saw it works in the non-slide presentation. Let me just leave, or let me copy the comma, right? Good idea, good suggestions, Ilya. Thank you very much. Oh, excuse me, it seems to be broken. Let me start it again.
Okay, so if you enter a comma, if you enter 2 arguments, then you get a matrix. Yeah? So this is a 3 times 5 matrix, 3 rows and 5 lines, and these will all be filled with random numbers. We will use this later, yeah. So keep this in mind. Yeah. So this could be, for instance, this could be 3 realizations of a random vector of length 5. Yeah, that typical data. Another important distribution is the standard normal distribution. Yeah, the one with the bell shape, yeah, that we just had, the Gaussian or standard normal distribution. One more thing. I don't know what happens here. Okay, that was the fruit sample. One thing I just want to note: you can also specify use another function use another function for there's also another function. If you don't want to sample from the interval 0 to 1, you have options as well to transform it manually. But you can also use this thing here, random uniform. This samples between 0 and 1 and creates a 3 by 5 matrix. Yeah, and might be a little bit more convenient because when you sample for, let's say you want to sample from 1 to 3, or sorry, let's say from 10 to 20 rather than 0 to 1, you could just enter 10 and 20 here, and then we will get uniformly distributed random numbers between 10 and 20. It doesn't matter, the performance is almost the same. Yeah, don't worry too much about it. I use this, I prefer this because I occasionally work with MATLAB or Octave, and there you have the same notation, and it's just a little bit easier for me. Okay, now the next distribution. What about the standard normal distribution? Now we want to draw from the bell-shaped distribution function from the standard normal distribution. And the method to do this is the method rand_n. Yeah? Rand for random and n for normal distribution. There's also an alternative choice where you enter the normal, same library, normal, and then you take the specify the mean. So this means a normal distribution with mean 0 and standard deviation 1. Yeah. The reason why I prefer this is this one is that I usually first thing is that you can use almost the same code in MATLAB or Octave, and the second thing is mathematicians usually specify the mean value is 0, that's fine, and the variance. And this specifies the mean value and the standard deviation. We will talk about standard deviation a bit later. Yeah, so this creates, again, if you sample only one vector, I will leave the comma. If you call it with one without argument, then you will get one random number. If you call it with one argument, you get in this case 3 random values, and if you specify more, then you can get it with more. Yeah, and you could also I still have the comma in my buffer. You can also make 3-dimensional arrays. Yeah, so that's that would be a cube of random numbers in a way. Okay. So what can you do with more complex distributions? Not everything is normally distributed or uniformly distributed, but there are also other methods. And I briefly mentioned that there's one method to sample from more complex distributions. If it's one-dimensional. If it's multidimensional, then we will talk about this afternoon. But one method is that you consider if you can take the integral over your probability density function, that's P, and if you can integrate it from -infinity to x. In some cases, the probability is 0 for negative numbers. We will see an example in a minute, but in many cases, it's like this. Yeah, it can also be defined for negative numbers, and this is the cumulative distribution function, which is the probability that your random number, yeah, this is the capital X, the random number that you sample will be below the value small x. Yeah, and this is just the integral. Yeah? By the definition of the probability density function, that's the integral from -infinity to x. And then there's an algorithm that helps you. If you can sample from a uniform distribution, then you can sample from a distribution which has this cumulative distribution function, or equivalently, probability density function that you are looking for. And this works like this. You draw a random variable from a uniform distribution. Yeah, this is just our function rand that we just saw in the next two previous slides. And then we invert this function. And let me show you one example. And I see that one I made one mistake with my slides, which I have to fix. Okay, so okay, then I stay in this presentation. Yeah? So let's take one example. Say we want to draw from an exponential distribution. What does exponential distribution mean? It means the probability density is 0 for x less than 0. So this exponentially distributed variable can never be negative, but it can be positive, and it decays. The larger the number, the less likely is that we select this number. It's easy to integrate the exponential function. Yeah, that's one of the integrals you learn at school probably. So the cumulative distribution function will be the integral from -infinity to x. And you see, because the integral at -infinity, the probability for values below 0 is actually 0. Yeah, so let me insert one thing to make this a little bit clear what happens here. One intermediate step. Oops. One intermediate step. So actually, because the probability is 0 below 0, this integral is actually an integral from 0 to x. Yeah. And this integral means this would be e to the minus x, minus e to the minus x minus e to the 0, and swapping the integrand, so that you see it's 1 minus e to the minus x. And if you invert, what we need to do, we have to, when we have a uniformly distributed random number, then we can just invert this. Yeah, so this is our u, and then we can solve for u, and then we see that f to the -1, so just the inverse function of this one, this is minus logarithm of 1 minus u. And actually, you can make it a little bit. You can use it this way, as I have done it here. So you sample a random uniformly distributed random number. So f of x, it must be a value between 0 and 1. Yeah. So it's the cumulative distribution that the probability that your value will be below the value of x, and the probability is certainly not less than 0, so it's between 0 and what is the upper limit? The probability can never become larger than 1, and if x goes to infinity, it must approach 1. Yeah. So and if you invert this, you sample you take your random number. Let's say it's 0.31. Then you subtract this number from 1. Getting 0.69, and then take the logarithm of it, and this will be a negative number, and then multiply this by -1. Yeah, actually you can do it a little bit simpler, because what is a uniform distribution of a number between 0 and 1? All values between 0 and 1 have the same probability. That's the same distribution as the distribution 1 minus u, or the distribution of 1 minus u. No? It's just reflecting this distribution. So we could actually take u rather than 1 minus u, because they are coming from the same distribution. Let's make a small example. Yeah, let's take 3,000 random numbers. We create 3,000 uniformly distributed random numbers. Yeah, so this is the uniform distribution, and then we take the logarithm of it. Yeah, so ln in most modern computer language is written as log. Yeah. And the decimal is log 10 usually. Yeah. And then we make a histogram of that. Yeah. And you see this the histogram. Actually, now we are taking. Maybe I should show you something if you haven't done histograms with matplotlib. Let me do it this way. If you just plot the histogram, then you get the actual number. Yeah, so we have created 3,000 random numbers, and around 600 of them, maybe 550, 70 or so, are in this very first small interval between 0 and I don't know, maybe 0.1. Yeah. So these are the absolute numbers, and if you want, in some, now I wanted to compute compare this to the density, and the density is something between 0 and 1. Yeah. So and so we want to have the frequency, the relative frequency, not the absolute frequency. Yeah? And you get this by typing. Giving the argument, keyword argument, density equals true. Yeah, then you get the relative frequency. So that means the probability density. Sorry, it's normalized to the interval slices. Yeah, so it's not the relative frequency. It does not mean that 80% are in this region, but 80% times the interval size here are. Have a value of in this interval, and you see it's fitting nicely to this exponential function. Yeah, just to make the point, we could have used this one minus u, and it leads to the same distribution because 1 minus u and u have the same distribution. You can think about it. It's quite easy to find out. Okay, I have a small exercise. Maybe we do this in the tutorials. We want to sample from a Cauchy distribution, and I got you some hints for that. Now let's come to the next topic that we need to know some knowledge we need to have to work with Monte Carlo methods, and that's some basic statistics. In stochastics, so we have to think about the concept of stochastic independence of two events x and 0. And I'm not sure what happened here. It's sorry about the glitches. Okay, sorry. These are some, the presentation style doesn't work in all cases completely great. So let me get back to this. Here. So let's say we have two events. So for instance, we sample a random number x and we sample another random number y. You could also think of rolling a die and then rolling it again. And these events are called independent when the probability that the event x occurs and the probability and the event y occurs. So this is usually written with a comma. So we have information about the event x and we have information that event y has happened. And this probability is just the probability that event x will occur and event y will occur. Yeah. For instance, let's say rolling dice twice. First, the probability that you roll the sequence 3 and 6. Yeah, that's the probability of rolling a 3, which is 1/6. Times the probability of rolling a 6, that's 1/6 again, so it's 1/36. Yeah. So if these are really Laplace dices, so we have real independence. Yeah. Another way to put it is in terms of the conditional probability. Conditional probability is defined as. Yeah, so we have information about the event y, and then we ask, what is the probability? Assume we know that we have rolled a 6 in the second attempt. What is the probability that we have rolled a 3 in the first attempt? You know, if they are independent, this should be. We cannot get information about this from the second die, rolling of the dice. Or we cannot infer something when we have rolled a 3 in the first attempt. We don't know. Then the probability of a 6 should be still 1/6. Huh? And the conditional probability, let's say, if we have the information about y, the conditional probability is written in this notation: P of x given y is the probability that these events will occur together divided by the probability of this event y that we have information about. Yeah, and if we have stochastic independence, then we know that we can factor this into P of X and times P of Y, and then these just cancel out. So this is just P of X, and this gives you that's another way to put it. So the probability of X given Y, because Y doesn't give us any information, it's just the probability of X. So information about Y doesn't provide any information about X. So another important thing that we need to know is the concept of an expectation value of a random variable. And we write this as, so this is now a random number, and or a function of a random number, and we want to take this expectation, and the expectation is defined as the outcome times the probability of the outcome, summed over all possible outcomes. That's for the for a discrete distribution. If you have a continuous distribution, you replace the sum over by an integral, and to replace P of X, the probability of X, by the probability density. But both are implementing the same concept, that you sum the integrals weighted by their probabilities. So you just sum up all events by their probabilities. And it's important to know that, or to keep in mind, that we never know the or usually in nature, when we are observing nature, we usually don't know the exact probabilities, and we don't know the exact expectation values. So we have to estimate the expectation. And statisticians usually write estimates with a hat over the symbol. So mu is for this lecture will always be the expectation of a value, and then there's a thing called the bar. This is usually an average. So an estimator for the expectation value is just the average. Very important concept for Monte Carlo methods. You take the average of data. If you have a sample, you can take the average by summing all values up and dividing them by the number of values. This is the same as weighting. Why is it the same as weighting? So the more likely events will occur more often. So let's, for instance, in the banana example, let's say banana is 0, apple is 1, cherry is 2, and 0 occurs with probability 0.6. So it's much more likely that in a sample the 0 will occur. It occurs with a higher probability, so it will show up in the sample. That reflects the probability. The frequency, that's the law of large numbers. The frequency of the random variable, the frequency of the outcome converges to the probability of the outcome, the relative frequency. And then for Monte Carlo methods, to understand Monte Carlo methods, we also need to understand the concept of variance. And what is the variance? The variance is okay, here we go. The variance is the expectation of the squared deviation from the mean, or rather from the expectation. Sorry, I should have written expectation. Mean is the estimator, the average, and the expectation is, in a way, the true value. So the variance, it's usually denoted as sigma squared, or another notation is variance of x. This is the difference between the deviation of the random variable. Sorry, now I have a serious error here. Put the wrong expectation. I should write it this way. So we take the difference between the random number and its mean expected value, and then square it, and then take the expectation of the squared deviation from the random from the expectation. And what you can show is that this is the expectation of x squared. Square the random variable, take the expectation, and you subtract the expectation squared. Be careful, it's not linear, so these are different values. It's only if they are independent events, then sorry, please forget that. But this is maybe you find this as the definition of the variance, but actually these are the same expressions. And be aware of the difference between the variance and the standard deviation. Standard deviation is the square root of that. That's basically it has the same dimension as the random number itself. It's a typical deviation from the mean. So if you draw your random numbers, you will have it will fluctuate by a certain amount from the mean value, and this certain amount is the standard deviation, and it's just the square root of the variance. There's also an estimator for that. Usually, for instance, in finance or in other applications, in biology, we want to measure in a way the variance, but the statisticians don't say measure; they measure it, but they estimate it. Never say you compute the expectation value, but you can estimate the expectation value when you are with statisticians. They will otherwise laugh about you and don't tell you why they are laughing. Oops. Sorry. So I'm lost in the okay, sorry. Until the break, maybe I stick to this. So how can we estimate it? The estimator of the variance is just idea of the mean is we take the average instead of the expectation, and we do the same thing here. We take the average squared distance from the estimator of the expectation, which will usually be the mean. And then we taking the average means we sum up the squared deviations and divide it by n. And if you had a proper statistics lecture, then statistics lecture, you may have seen that it's usually replaced with n-1. That actually both are valid estimators, but for the case of the normal distribution, this will be this will be the maximum. What we have here is the so-called maximum likelihood estimator, but it's a biased estimator, and you have to divide it by n-1. Then it's becoming an unbiased estimator. But my main focus here is Monte Carlo. I won't talk too much about, but both have their use. Yeah, both estimators with n or n-1. But for Monte Carlo methods, we are usually talking about numbers, thousands of observations. So n will be typically in this 100,000 or thousands or even millions. So this doesn't matter too much for us. Yeah, and if you have the sequence itself, then you can use the we will make use of that in the Monte Carlo part. You can use numpy.var or numpy.std to get the variance or the standard deviation. And maybe we should do in the tutorial some exercises about this to see this working, yeah? And to get a bit more comfortable with it. But sorry about a little bit of theory again. I want to show you some one important result from statistics that we definitely need for Monte Carlo methods. And it's a statement about the sum of independent random variables. Let's say x and y are random variables. We draw random variables, and now we take the sum of them. And we need a technical assumption that we can take the expectation value of x squared and the expectation value of y squared. It's a technical assumption, so-called the second moment of the distribution must exist. That's the case in most applications, but not all. There's some applications in physics and where you have it basically means that you don't have a large probability of extreme events. That's basically behind this assumption. So take this as a technical assumption that is valid in most applications, but maybe if there are extreme events, it may be, the situation may be different. If there's a considerable probability of extremely high values. What is the expectation of the sum of two random variables? I guess you will not be too surprised when I say due to the linearity of the expectation, it's a linear function. The expectation value of the sum is the sum of the expectation values. I guess nobody would say, oh, wow, I didn't expect that. What is a little bit more difficult to see, and unfortunately due to lack of time, I cannot show it to you, but it's not very complicated math, that the variances of the of x plus y is actually the variance of x plus the variance of y. Now that's maybe that may be a little bit more surprising, because we are taking squares here, yeah, and this has some important consequences. So same is true for three random variables. Yeah, if we sum up three random variables, the expectations will sum up and the variances will sum up. And if we have n variables, and now let's assume that these are independently drawn from the same distribution. That's an important concept. I hear that not all have a math, physics, statistics background. This is called IID. Yeah, so we have independent and identically distributed random variables. Yeah, so all are drawn from the same distribution, but independently. Yeah, like think of rolling a die. Rolling dice, yeah, or throwing coins, throwing fair coins. Then the expectation of the sum will be n times the expectation of a single event. The expectation of the variance will be n times the expectation of n times the variance of this distribution. And this means that the standard deviations will grow with, well, because we have to take the square root of this. The standard deviation is the square root of the variance. And this makes the standard deviation grow with a factor square root of n. Now, this is this famous square root law that you may have heard about in your statistics classes. But keep in mind, and it's important to keep this in mind, that this draws on the independence. Yeah? So the additivity of the expectation value, this holds without independence, but the variances add up if the values are independent. And actually, we can say a little bit more. There's the famous central limit theorem. Yeah, so this will be the last theoretical part. So I'm very sorry for that. Not everybody loves theory so much, but we can say something about the sum and about the averages. Yeah, so here we have the mean. The mean is just the sum divided by n. Yeah, so it's a sum of random variables. And if we sum up these random variables, one can show that the sum is basically converging to a normal distribution. Yeah, the sum will converge to a normal distribution with mean n times mu and variance n times sigma squared. Or usually you find it in this formulation. If you take the mean and look how much is the mean value apart from how far away is the mean value from the real expected from the real expectation mu. Yeah, so in a way, this is the error of the mean. And if you multiply this error of the mean by square root of n, this will converge in distribution, whatever this means. Don't worry. It just means if n is getting bigger and bigger, you're getting closer and closer to a normal distribution with mean and 0 and variance sigma squared. Or you can formulate it in another way. The error of the sample mean, and we need this for Monte Carlo method later, is asymptotically normally distributed with a standard error of sigma divided by square root of n. Yeah? It's just taking this square root of n to the other right-hand side of the equation. Now, this means if you increase your sample size and you want to estimate the expectation, then the mean is getting better and better in approximating the expectation, and the error that you make is getting smaller and smaller, and it's getting smaller by a factor of square root of n every time you increase when you increase your sample size. And I want to show you this central theorem at work now. Yeah. So let's do the following. As a distribution, I take, I will now draw 1 million random variables from a uniform distribution. And then I plot the histogram. Yeah, I sample a matrix. So this has 1 million columns. By the way, I don't know if you know that in Python, you can separate zeros or separate anything with underscores. Yeah. So for instance, it's easier to read that this is 1 million if you use underscores. No? I think that's a very nice feature. of Python. And I miss this in other languages, some other languages. Yeah, so D is if D is 1, this will be just a one-dimensional n 1 million 1 million times 1 vector. Yeah, and I plotted it here. Yeah, so this is the start. So this is a uniform distribution. We see that looks really nice. So we have 1 million random numbers, and the bin size is 100. So in every bin, there should be about 10,000 random values. Yeah, this is the distribution of one of these IID random numbers. Now let's take 2 of these random numbers and add them together. And think for a moment what you would expect. So I draw 2 random numbers independently. Let's say the first one is around here, 0.15, let's say, and the second one is here, 0.6, let's say, yeah. And the sum will be 0.75. But in principle, it could also be but this is less likely, that we draw 2 numbers that are very close to 0. Or we could have 2 numbers very close to 1. So the sum will be between 0 and 2. Yeah? Because if we happen to draw 2 numbers from this interval here, the sum will be 2. Yeah? So the output, the sum will be in a larger range between 0 and 2. What will be the distribution? What do you think? Unfortunately, I cannot get replies from you, but yeah, probably you see, if I have a large one, a small one here, and a large one here, I will get up here, get here. Yeah, I show you the what comes out if I add these 2 of these. Yeah, and this looks like a triangle, and actually it is a triangle. And you see the distribution will be between 0 and 2. Largest possible value, and some of these are coming close to that, is 2. But it's quite unlikely that I have values of 2, because I have to draw independently 2 numbers which are very, very close to 1. And I think it's easy to understand that that it should be that the probability to have a sum that these values sum up to 1, that this is higher than that the numbers will up to 0 or 2. Now, it's a little bit harder to see that it's actually a triangle shaped distribution, and the analytical solution is it actually is a triangle. Yeah? We see some small deviations because we sample only a finite size, but if we sample more of them, it will become get closer and closer to this triangle. Yeah? You see, there we are already pretty close. And the result of yes, 1 second. I'm just in a lecture for 3 more minutes. Yeah, yeah. Sorry. The central limit theorem says if I add more and more, let's say 3 random numbers, I should come closer to the Gaussian. And you see now it extends from 0 to 3 as I expect, and you see it's becoming a little bit more bell-shaped. And the higher the number, if I add 4, it will be between 0 and 4. Yeah? So the highest possible value is 4, but this is already pretty unlikely. Yeah? That you have 4 numbers independently from this, that all 4 summons are very close to 1. And the higher you select this value, the closer you really come to a normal distribution. Yeah, and for let's say 15, you cannot distinguish it practically from a normal distribution for most practical purposes. Yeah, Okay, so that's the meaning of sorry, this ends this introductory part about statistics. I told you some results that we need for the Monte Carlo part in the afternoon. Let me see at the chat whether there are questions that I can answer now. But yeah, so keep this in mind. The sum of random variables, whatever, I could have started with a triangle actually, and the sum of all these triangly distributed random numbers, they will also converge to this distribution that I've shown you, to a normal distribution. Also, we can now add up exponentially distributed random numbers, and again we have the same result. Yeah, so because all these fulfill this technical condition. Yeah, so keep in mind the sum and the average, the mean, is a sum divided by a value. The sum converges to a Gaussian distribution, and this is very helpful, as we see we'll see in the afternoon when we will discuss Monte Carlo methods. Okay, so I understand that I'm now at the end of my talk, and we have a break now for half an hour, I think, and then we look into the tutorials. And I encourage you to use the chat such that we can discuss some of these concepts, yeah, and also make some experiments with random numbers and random data. Okay, thank you very much, and that's it from my side.
Thank you very much, Uwe. And now we'll have a break for half an hour. Thank you.